final example we're going to do is an incredibly important example of a vector field. One that comes from just a normal old scalar function f of x, y, and z. A function from R3 in this case, just to R. Well, for such a scalar function, you could take what we called previously in multivariable calculus the gradient. The I hat component is the partial with respect to x, the y hat is the partial with respect to y, and the k hat is the partial with respect to z. That is, if you give me a scalar function f from either R2 or R3 to R, then I can give you a vector field, a corresponding vector field given by the gradient of f. The gradient of f is a vector field. And it also has a very nice geometric meaning. So for example, suppose that my function was the function f of xy equal to x squared plus y squared. Then we could compute out what its gradient is, not too bad. Well, the partial with respect to x is just 2x, and the partial with respect to y is just 2y. So the gradient is just that. Now, we've seen this vector field, except for the fact that there's a 2 in both places, which just stretches every vector by a multiple of 2. This is precisely the vector field we saw earlier. And so now I can put everything together in one picture. So this is my picture for this function. What we see is the graph of the function. That's this blue paraboloid. And then in the domain is the xy plane, we get a vector field in that domain. And so I've plotted the gradient vector field in the domain and then this function above the domain. And as you might recall from multivariable calculus, the gradient vector points in the direction of steepest increase of your function. So if you're at some particular x and y coordinate and you're up there on the function value at that x and y coordinate, you want to know, how do I climb this mountain represented by this function as fast as possible? Where is this function steepest? What direction should I go? You should go in the direction of the gradient.